There is a wall around our solar system. We know it's there. We can prove it's there. And in 69 years of spaceflight, humanity has never come remotely close to touching it. Not Voyager, not New Horizons, not anything we have ever built or launched. We call it the Oort Cloud, and it is so far away that our fastest, farthest traveling machine, moving at over 61,000 kilometers per hour, after almost half a century of continuous flight, would need another 300 years just to reach its inner edge. Not to cross it, just to touch it. This is a story about a boundary we cannot see, cannot visit, and may never reach. It's a story about scale so extreme it breaks the human sense of distance entirely. And it starts with a number most people get wrong the moment they hear it. Ask most people where the edge of the solar system is, and they'll say Pluto. Ask a slightly better informed person, and they'll say the Kuiper belt, that flat ring of icy debris past Neptune where Pluto and its cousins drift. Ask NASA, and the answer is different. The Kuiper belt isn't the edge. It's not even close. The real edge, the true gravitational boundary of the Sun's influence, lies in a spherical shell of trillions of icy objects that begins roughly 2,000 to 5,000 times farther from the Sun than Earth is, and doesn't end until somewhere between 50,000 and 200,000 times that distance. We call it the Oort Cloud. And here's the part that should stop you. We have never seen it. Not one image. Not one direct detection. Every single thing we know about it comes from indirect evidence, from watching where comets come from and doing the math backward. That's where this story turns. Let's put real numbers on this, because numbers are the only thing that make this comprehensible. Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun, 30 times the Earth-Sun distance. Voyager 1, launched in 1977, has been flying outward for nearly 50 years at a speed that would circle the Earth in under 40 minutes. As of 2026, it sits at roughly 170 astronomical units. That sounds enormous. It is enormous by any human measure. But here's the turn. The inner edge of the Oort Cloud doesn't begin until somewhere around 2,000 to 5,000 astronomical units. Voyager 1, our single farthest reaching object, our 50-year triumph of engineering, has covered less than a tenth of the distance to even the closest edge of that boundary. Picture it like this. If the Sun were a street lamp and Earth were a pebble 1 meter away, Voyager 1, after nearly half a century of travel, would only just now be crossing the street. The Oort Cloud's inner wall would still be almost 2 kilometers farther on, and its outer edge, where the Sun's gravity finally loosens its grip entirely, that's not a walk. That's a different city. If you were watching this thinking humanity is close to the edge of its own home, you are not. We are barely past the driveway. And the driveway keeps going. The outer edge of the Oort Cloud sits somewhere between 50,000 and 200,000 astronomical units out, roughly 0.8 to 3 light years from where you're sitting right now. Light itself, moving at nearly 300,000 kilometers per second, needs somewhere between 10 and 28 days just to reach the inner wall of that region, and up to a year and a half to reach the outer one. Sunlight leaving the Sun's surface right now won't finish crossing the Oort Cloud until sometime after most of the people alive today have died of old age. Most people assume this story starts with the astronomer whose name got attached to it. It doesn't. In 1932, an Estonian astronomer named Ernst Pick looked at the same puzzle that would eventually make headlines 18 years later. the strange, scattered orbits of long-period comets and proposed that they came from a vast, distant reservoir surrounding the Sun. He built on earlier statistical work from 1907 by Armin Otto Leuschner, who had already noticed something odd in how comet orbits clustered. Pick did the math. He got there first. But turn the page 18 years forward, and a different name is the one you'll find in every textbook. In 1950, Dutch astronomer Jan Oort published his own statistical analysis of long-period comet orbits, arriving independently at a strikingly similar conclusion, and it's his name, not Pick's, that stuck to the cloud. Most people who've heard of the Oort Cloud have never heard of the man who proposed it first. That's not just a historical footnote. It's a pattern worth remembering, because it happens again and again in the story of how we came to understand the edge of our solar system. The person who does the pioneering work often isn't the one history credits. And if that's true of a name in a textbook, it should make you wonder what else about this boundary has been simplified, flattened, or half forgotten on the way to the version we were taught in school. Here's a fact that almost never makes it into the popular version of this story. When Oort ran his 1950 analysis, he wasn't just proposing a vague cloud out there. He found something specific. The orbits of long-period comets, when traced back to their farthest point from the Sun, clustered strongly around 20 astronomical units. That number, 20,000 AU, became the anchor for his entire theory of a spherical, isotropic reservoir surrounding the Sun in every direction. But buried in that same data set was something stranger. A smaller group of comets showed farthest points closer to 10,000 AU, roughly half the distance, and their orbits looked disturbed, as if something had already tugged them inward during an earlier pass through the inner solar system. In other words, even in Oort's original data, there were signs that this reservoir wasn't static. Objects were being kicked loose, pulled inward, and sent on new paths, evidence of a slow, ongoing churn happening across a timescale of millions of years, entirely invisible to us, entirely inferred from orbital math alone. Every long-period comet that streaks across our sky today carries a piece of that story. Each one is a message from a place we have never seen, describing a disturbance that happened before any human civilization existed to record it. Here's a fact with no framing attached to it at all. The last comet visible to the naked eye traveled for millions of years to reach a sky that for most of that journey had no one in it to look up. By the 1980s, someone finally asked the obvious question: could we actually go there? In the early 1980s, engineers at NASA's Jet Propulsion Laboratory studied a real mission concept called TAU, 1,000 astronomical units. It called for a nuclear electric propulsion spacecraft designed to reach 1,000 AU, deep into the inner edge of Oort Cloud territory within 50 years. To do that, it would need to reach a velocity of roughly 106 kilometers per second, several times faster than anything humanity has ever launched. It would have carried a 1-meter optical telescope and a 10-watt laser transponder designed to beam data back across that unimaginable gulf at a crawling 20 kilobits per second. It was never funded. It was never built. It never left the drawing board. And here's the turn. Even if it had launched, even if every system had worked flawlessly for half a century straight, TAU would have arrived at 1,000 AU, still short of the Oort Cloud's inner edge, still decades away from the boundary it was named for. We studied, on paper, a mission 4 times faster than anything we've ever flown, and it still wouldn't have been enough. If our most ambitious unbuilt spacecraft falls short, what does that tell you about the machines we actually have flying today? The Oort Cloud isn't even one single uniform shape. It has architecture, layers we've had to theorize just to make the comet data make sense. In 1981, Los Alamos astronomer Jack Hills proposed something the original 1950 model didn't account for: a denser, disk-shaped inner region, aligned roughly with the plane of the planets, spanning from about 2,000 out to 20,000 astronomical units. We now call it the Hills Cloud. It's thought to contain tens to hundreds of times more comets than the outer spherical Oort Cloud that gets all the attention, and it may be the reservoir that keeps quietly refilling the outer cloud, comet by comet, over billions of years. So the edge of the solar system isn't a wall. It's at least two structures nested inside each other. One dense and disk-shaped, one sparse and spherical, both invisible, both inferred, both never once directly observed. Take a breath here, because the next part gets stranger. In 2016, a team of researchers tried something almost desperate. If we can't see these objects directly, maybe we could catch their shadows. They combed through 1.6 million seconds, over 18 days' worth of archival data from the Rossi X-ray Timing Explorer, a satellite originally built to study neutron stars and black holes. Their plan: watch two bright X-ray sources continuously, and wait for the flicker of an Oort Cloud object passing in front of one of them, blocking the X-rays for a fraction of a second. They found nothing, not a single occultation, in 18 days of continuous watching. Here's the turn: that nothing was still useful, because it let them calculate an upper limit on how many small objects could possibly be out there, and that upper limit came in orders of magnitude higher than what theoretical models predicted. In plain terms, we still don't know with any real confidence how much matter is actually floating in that boundary. Our best statistical tools can rule out almost nothing. The region remains, functionally, a blind spot the size of a light year. We built a machine to watch the edge of our own solar system for the shadow of anything at all, and after 18 days, it saw only stars. Sometimes the disturbance isn't ancient. Sometimes it's recent enough to still be affecting the sky above you right now. Data from the European Gaia Space Telescope suggests that a Sun-like star, catalogued as HD 7977, passed within roughly 6 to 10,000 astronomical units of our solar system about 2.47 million years ago. That's close enough in the context of the Oort Cloud's true scale to have physically disturbed its inner region, kicking loose a wave of comets that, according to some researchers' estimates, may still be arriving today at roughly twice the long-term average rate. Every extra long-period comet crossing our sky this decade may be an afterimage of a stellar flyby that happened before modern humans existed as a species. A star came close enough to brush against the edge of our home, and we are, quite possibly, still catching the falling debris from that encounter 2.5 million years later. Now for the part almost everyone gets wrong, including, for a long time, mission planners themselves. When Voyager 1 crossed the heliopause in 2012, the boundary where the Sun's outward stream of charged particles finally gives way to interstellar plasma, headlines everywhere declared that it had left the solar system. It hadn't. The heliopause is a boundary of solar wind pressure, not gravity. Voyager 1 is flying through interstellar space, technically, chemically, in terms of the particles now around it, but it remains gravitationally bound to the Sun, still centuries away from even the closest edge of the Oort Cloud, which is the true dynamical boundary, the point beyond which an object is no longer held by the sun's gravity at all. The Kuiper belt gets confused with this too. It's a flat disk of icy debris just past Neptune out to roughly 50 AU, a neighborhood, in Oort Cloud terms. The Oort Cloud starts where the Kuiper belt's story has already ended, thousands of AU farther out, in a completely different shape, a sphere instead of a disk, built from a completely different formation history. Voyager 1 left the sun's atmosphere. It did not leave the sun's grip. There is one directly observed object that hints at what lies between here and there. Sedna, discovered in 2003, is roughly 1,000 kilometers wide, with an orbit that swings from about 76 astronomical units at its closest to the Sun out past 900 astronomical units at its farthest. Standard models, the ones explaining most Kuiper belt objects through simple gravitational scattering by the giant planets, struggle to fully explain how something like Sedna got parked on such an extreme, detached path. Some researchers think it's a messenger from the true inner edge of the Oort Cloud on an orbit that occasionally, briefly, brings a piece of that distant world close enough for us to actually photograph. It is the closest thing we have to physical evidence from the boundary itself. One object photographed out of an estimated trillion. The total population of the Oort Cloud is thought to run into the trillions of icy bodies, adding up to somewhere between 10 and 100 Earth masses of material, almost all of it smaller than 100 kilometers across, scattered so thinly across such an enormous volume that kilometer-sized objects can sit tens of millions of kilometers apart. Calling it a cloud barely fits. It's closer to a handful of grains of sand thrown across the volume of an entire solar system. How do trillions of objects amount to less mass than 100 Earths? Because almost none of that volume has anything in it at all. Even if we solved every problem of speed tomorrow, there's a second wall waiting behind the first one, and it's not about distance at all. The Voyager probes and every deep space mission since run on radioisotope thermoelectric generators, RTGs, powered by plutonium-238. That isotope has a half-life of only about 88 years. Do the math on a 300-year journey to the Oort Cloud's inner edge, and the power source would have decayed through more than 3 full half-lives before arrival, reduced to a fraction of a percent of its original output, nowhere near enough to run a transmitter, a camera, or anything else. The spacecraft wouldn't just arrive late. It would arrive dead decades or centuries before it ever got there, a silent hull drifting the rest of the way on momentum alone. Alternative fuels exist. Americium-241 lasts far longer, but it produces less power per kilogram, which means more mass, which means more fuel, which means a heavier, slower spacecraft that takes even longer to get there. Every fix for one problem makes the other problem worse. No current mission design has solved this trade-off. Not on paper, not even theoretically. We are not just too slow to reach the Oort Cloud. We cannot yet build anything that would still be alive when it got there. So where does that leave the theory itself? The existence of the Oort Cloud isn't in serious doubt. The isotropic arrival of long-period comets from every direction in the sky is well explained by nothing else. But almost everything about its details remains an open argument. Some researchers, like Simon Porteous-Zwart, argue that the Sun's early birth cluster, a dense stellar nursery packed with roughly 14 solar masses per cubic parsec, which dissolved within about 1 billion years, played a far stronger role in shaping the cloud than standard models allow, and that clouds forming early in that crowded environment lose as much as 85% of their comets to the surrounding chaos before ever settling into their final, quiet orbits. And then there's the more contested claim. Some scientists, led by Konstantin Batygin and Mike Brown, argue that the unusual clustering of extreme trans-Neptunian objects points to an undiscovered Planet 9 quietly reshaping the inner Oort Cloud structure from the shadows. Others argue the clustering is nothing more than an artifact of where and how we've been looking, observational bias dressed up as discovery. No one has settled it. No one currently can. We opened this by saying there's a wall around our solar system, one we've never come close to touching. That's still true. Voyager 1, our best and farthest reach, needs 3 more centuries just to arrive at its threshold, and 30,000 years to fully cross it, a span of time longer than all of recorded human history, several times over, just to pass through a boundary we can't even confirm the size of. Pick proposed it. Oort's name stuck to it. Hills found a second layer inside it. A star we'll never see swept past it 2.5 million years ago and may still be shaking comets loose today. And still, after all of that, the 2 questions that matter most: how much is actually out there, and what, if anything, is quietly rearranging it from within, remain exactly where they were, unanswered, unresolved, and for now, unreachable, somewhere out past 2,000 astronomical units, in the cold and the dark and the near-total emptiness. The true edge of home is waiting. We know it's there. We can prove it's there. We have absolutely no idea when or if we will ever see it for ourselves.